Welcome back. In this video, I will be discussing dot point 11.10, which looks at the interpretation of the results in mainly HPLC, but I'll spend some time talking about paper chromatography as well. Okay, so when we talk about the different chromatography techniques, essentially there are two types, and as I mentioned earlier, chromatography could be considered qualitative. So if you talk about paper or thin layer chromatography, those two techniques would be purely qualitative because they cannot tell you the concentration of each substance in the mixture. However, column and high performance liquid chromatography would be considered quantitative techniques as well as qualitative because you can, from the result, work out exactly the concentration of each substance. And in fact, HPLC or high performance liquid chromatography is used very often to determine the concentration of something. Okay, let's just quickly look at paper chromatography, which I can guarantee you're not going to get something this easy. But anyway, it's always good fun. So your stationary phase is a solid or a solid that is coated with a viscous liquid. Now, classic example, which is paper chromatography, would be just, filter paper, but you can have a piece of silica with really finely milled powder on top. The mobile phase is a solvent, usually water, and the origin. So when you start the experiment, you're going to draw a line, definitely in pencil, not in pen. Don't make that mistake. That's just good. The ink just going to go everywhere. So you're going to draw a line that is called the origin, and this is where you're supposed to load your sample. So in this particular example, there are 3 dots that are being loaded, 3 ink colors, if you will. So we have green, orange, and purple. And so the sample are loaded here, and what is going to happen is the water is going to rise up the paper, or if you want to sound fancy, the mobile phase is traveling up the stationary phase, and as it does so, it's going to carry the sample with it. And you're going to stop when the solvent front is reached at around here. So the solvent front is the name to the point or the line, if you will, that is reached by the mobile phase. And the idea is you want to stop just before it reaches the end of the paper so you can pick it up and doesn't crumble into pieces. And obviously the mobile phase is going to travel the longest distance in this case, but you can see that different components of the mixture are being separated here. You can see that the purple one is red and blue, and then the orange is red and yellow, and the green is yellow and blue. And the 2 blue should have the same distance, and the 2 red the same, as well as the 2 yellow. So you can see that each of these colors is actually a mixture of 2 different primary colors. Okay, so another way to further quantify the result of a paper chromatography or a thin layer chromatography experiment is to calculate what is called the retardation factor, and that is just a ratio between the distance moved by the component and the distance moved by the mobile phase or the solvent front. So this is another example of a chromatogram, which is what you get after you finish the experiment. And the solvent front in this case 8.5 centimeter, and then you have the 2 samples at these 2 different distance traveled, and you can work out the ratio from there. So obviously the retardation factor, or RF, has to be less than 1 because the sample cannot move further than the mobile phase. And the good thing about the retardation factor is that if you have a set of standards, so for example, if you are testing for the components in ink, if you have an idea of what are the things that are usually used in ink, you could run those standard pure samples and compare the retardation factor of those samples with your unknown, and that may allow you to identify what substance or substances are in the ink. So I think I wrote it in here. So under the same condition, with the same procedure, if a compound shares the same RF with a standard, the compound is very likely to be that standard. So this is the feature of chromatography that allows you to identify the name of a substance. So in this sense, RF is a unique and a constant for compound. However, in order for this to actually be done, you need to make sure that the standard experiment is run under the same condition with the same procedure compared to the experiment that was used to determine the unknown. So the 2 experiments have to be of the same conditions for the comparison to be valid. All right, that's enough reminiscing about paper chromatography. What is the focus of this year is really on HPLC, or high performance liquid chromatography. Some also say high pressure liquid chromatography, which it's fine. I mean, it does have a pump. So this is what it may look like. This type of chromatography technique is a lot more sensitive, a lot more accurate, and the machine is also a lot more expensive. Now you still have your basic, which are your stationary phase and your mobile phase. So the stationary phase in this case is a column in the machine, and normally the column is going to be packed with a waxy porous substance, or you can have really long chain hydrocarbons. So the key here is that the column is being coated with very, very small particles, which allows for adsorption and desorption to occur very quickly and makes it really hard, if you will, for the substance to go through the column. So because of that, it's going to make the separation a lot better. Now the mobile phase in this case is a liquid because it's high performance liquid chromatography. There's a technique that used to be in the course, but they removed it, called gas chromatography, and that's when you use a gas as a mobile phase and you use it to determine gas compositions in, say, air mixture or even perfumes and things like that. But anyway, if it's HPLC, the mobile phase would be a liquid, has a name called the eluent, and I'm pretty sure I pronounced that incorrectly. It's going to elute through the column. So elute, one of those words. I should know how to speak English. But basically what this means is you can think of an example of eluting is when you wash, say, your chopping board and there's like stuck on the chopping board. Let's say you just cut, I don't know, what do you cut that will stick onto the chopping board? You know, it could be meat, it could be, if you don't eat meat, cheese. Would cheese stick onto the chopping board? Anyway, so let's say there's food stuck onto the chopping board and you run the chopping board underwater. That's what eluting means. So it's basically having water running through a surface, and that water is going to carry any of the bits off the surface. So that's what eluting is. Cannot believe I spent that long trying to come up with an example of elute. So the mobile phase is going to elute through the column, and you have to say it with an accent, and it's going to carry the sample with it. So if you look at this, it's actually a very interesting design because the mobile phase is introduced first, and because the column is very tightly packed and this is a liquid, in order just to give it a little bit of a kick, you normally have a pump here, so hence the name high pressure as an alternative. So the liquid is going to be introduced with high pressure into the column, and as it does so, you have the sample being introduced with it. And then everything is going to come out. So obviously the first thing that will come out is the mobile phase, and then the substances in the mixture will gradually come out as well, and it will get detected and recorded. So that's high performance liquid chromatography. This is what the machine can look like. Now there are so many different designs for HPLC and different levels of sensitivity, different price tag. They're all very expensive that we can't afford. But really what you need to do, and even when you go to university or you work in a lab, most of the time you have to be able to analyze the result. And there's very little that you have to do when it comes to the machine except for putting in the sample. So let's talk about the result. Before that, so two types of HPLC. Normal phase HPLC, which is not the common method these days. You would have a polar stationary phase and a non-polar mobile phase, and then reverse phase HPLC, which is actually the more popular method. This is the one that I discussed in the previous video, which has a non-polar stationary phase, and the mobile phase in this case will be polar. Okay, so this is what the result looks like. You need to be able to read it and understand what's going on and then use it. So this is called a chromatogram. So very similar to NMR, there will be a few features that you need to pay attention to. The first one, again, would be the number of peaks, and in this case, it is a representation of the number of molecules in a mixture. So if there are 1, 2, 3, 4, 5, 6 peaks, there are 6 different molecules present in that mixture. Okay. Remember that chromatography is a technique used to separate substances in a mixture. So you always start with a mixture. If you have a pure substance, you should only see 1 peak. So it is also a very good technique to identify whether your substance is pure or not, depending on how many peaks you will see. The second feature that you need to look at would be the horizontal axis, which represents retention time. So retention time is the horizontal axis, also known as RT, and Basically, it records how long it takes for each component to exit the column. And the vertical axis, which depending on the chromatogram that you read, can either say peak height or peak area of absorbance or abundance, as in this particular example. And it is a measure of the concentration of each molecule in the sample. So if I look at this, I know that this particular molecule is in a much lower quantity than this particular molecule. All right. So the horizontal axis will give you information on the degree of adsorption, whereas the vertical axis gives you information on the amount of each substance in the mixture. All right, so let's talk about the horizontal axis of retention time. I don't think I need to make a slide on the number of peaks. It's pretty self-explanatory. But the retention time, so as I just said, it indicates the degree of adsorption of each molecule. The more strongly adsorbed a molecule is, the higher its retention time is going to be. So the one with high RT, which are the one that span longer in the column, are the one that are more attracted to the column. High RT is the same as high adsorption. So the difference between HPLC and paper chromatography, it's mainly that in the case of paper, you keep the time the same and then you measure the distance traveled. Whereas in the case of HPLC, you keep the distance traveled the same and you measure the time. And in both cases, the thing that affects your result is actually the speed, which I mentioned in the principal video. Now, this is also where the qualitative feature of HPLC comes in. Once you have the retention time of an unknown molecule, you can compare it against the retention times of standard known pure compounds. So this is done a lot, especially in, say, blood analysis, because there are certain things that you look for. So if, say, for example, you want to determine whether ethanol or alcohol is present in someone's blood or some illicit drugs, you should already know the retention times of those molecules, and it would very quickly allow you to determine whether or not those illicit substances or alcohol are present in a person's blood, not drug. Okay, so this also requires that the retention time of the standard and the retention time of the sample are obtained under the same conditions using the same procedure. So that's standard. So if you have a standard, then you want to make sure that when you analyze a sample that the same conditions are being adhered to. All right, so that's retention time. Now, sometimes you may have molecules that have very, very similar retention times. This is not normally the case with macromolecules because they tend to have very different structures. So the degree of adsorption and the type of interactions that they have with the stationary phase tend to vary so much that it's actually quite difficult to get two molecules with very similar retention times. But when that happens, there are things that you can do to try to separate two molecules a little bit better. So you can either do that by packing the column with smaller particles. So instead of the first case, we're going to the second case. So if you pack them with smaller particles, it would make it harder for things to go through, and hopefully that allows you to achieve the separation. Or you can increase the length of the column. So simply by making them go for a longer distance, you would be able to make the separation occur, I guess. However, obviously, it's hard to actually increase the size of a column if you have a machine already. So the third method is also quite popular. Is when you just simply decrease the pressure. So you make them all go a little bit more slowly, and hopefully that allows the separation to take place. I'm not entirely sure what I'm trying to say here with these two diagrams, but it's supposed to be decreasing pressure. All right, so that is the retention time. Now, if we talk about the vertical axis, so either peak height, peak area, absorbance, depending on the chromatogram that you look at, it will give you a measure of the abundance or the concentration of each molecule in the sample. All right, so in order to actually go from that reading, which is the height or the area or the abundance, to the concentration, you need to use what is called a calibration graph. So you definitely have seen this last year, so this is just a quick recap. So this is a snapshot of what the whole technique looks like. You need to prepare your standard solutions, make a calibration graph, and then you can do your reading. All right, so let's just start with the calibration graph. I used to call it calibration curve, but then people got super confused because it's a straight line. I'm not going to go into why it's a curve at this point, but anyway. So if you want to prepare a calibration graph, first of all, you need to focus on one substance. So you can't analyze the concentrations of multiple different substances using the same calibration graph. So for example, if I want to determine the concentration of ethanol, that's one thing. I already know what the retention time of ethanol is, so I've already identified it in my chromatogram. What I'm going to do now is to create a calibration graph specifically for ethanol. If you want to determine the concentration of, say, dimorphin, you would need a different calibration graph. Now, some of you may know what dimorphin actually is. Anyway, so in order to prepare a calibration graph, the first thing is to actually have standard solutions. Now, standard solutions are just names, well, the fancy way of calling a solution that I know the concentration of. So you need to prepare a set of standard solutions. So in this case, if I'm trying to create a calibration graph for ethanol, I need to prepare a set of ethanol standard solutions. So solutions with known ethanol concentration. Now, the concentration in this particular example is being reported as volume per percentage volume per volume, which is just another fancy way of saying how many ml of ethanol per 100 ml of solution. So percentage V over V is the same as milliliter per milliliter 100 ml of solution, which is actually the way that ethanol is normally reported in alcoholic beverages. So it's normally percentage V by V. The blood alcohol concentration is actually percentage grams per volume. So anyway, I start getting sidetracked again. So you have four standard solutions of varying concentrations. What you're going to do is you're going to analyze them using the same HPLC machine that you used previously to analyze your unknown sample. Again, you need the same conditions, the same pressure and temperature and all of that. So once you've done that, you're going to determine the peak area of each standard solution. So the one at 4% volume by volume has an area or higher, no area in this case, of 16, and then the 3 is 12, and then the 2 is 8, and the 1 is 4. So these are actually going to be the point coordinates for your graph. So concentration is going to be the independent variable, and peak area is going to be the dependent variable. You actually can't see me, but I'm doing like a dependent dance as of right now. So there are 4 points. First one's going to be 1, 4, concentration of 1, area 4. The second is going to be 2, 8. Now this is a hypothetical situation. In reality, you're probably not going to have a perfect linear relationship. So 3, 12 and 4, 16. Okay, so once you have determined the peak area of each of the standard solution, you're going to plot your calibration graph. And please, let's hope that nobody is going to make this mistake, because I used to have this student who made the same mistake in year 11 and 12, no matter how many times I told her. But the horizontal axis has to be your concentration. Just think about it. Concentration would control the peak area, or peak area depends on concentration. So the dependent variable should be the vertical axis, that's your peak area, and the concentration is the horizontal axis. So you're going to plot your 4 points. So you have your 1, 4, 2, 8, 3, 12, and 4, 16 here. Now this is a perfect linear relationship. In reality, you're probably going to need to draw a trend line or line of best fit. Also in reality, this normally is done in Excel, so you just need to put your scatter plot and then do a trend line and then work out the equation of that trend line. But that's going to be your calibration graph, this particular line. Once you've got your calibration graph, you then can use it to determine the concentration of the unknown. So this is my unknown. So I don't know what concentration it is, but from the graph, I can work out the peak area. So this is just simply a matter of reading a graph. So you start with, you're given the y coordinate and you need to work out the x coordinate, which in this perfect example works out to be 2.5% volume by volume. And that is how, generally speaking, calibration graph is used to determine concentration. I just have 2 things I want to point out, or maybe 3, when it comes to using a calibration graph. So the first one is you absolutely are not allowed to extrapolate when you have a calibration graph. I mean, I'm not gonna generalize that you can never extrapolate. Like if you actually extrapolate, police will be knocking on your door or anything, but it actually decreases the accuracy of the technique a lot if you have to do extrapolation. Ideally, you don't extrapolate. So you want to make sure that when you create a calibration graph, that the peak area range or the concentration range of your standard solutions actually cover the concentration of the unknown. So the concentration of the unknown has to be somewhere between 0 and 4% volume by volume in this particular example, or you want to make sure that the peak area of your calibration graph is going to cover this. So if I have a unknown with peak area of 20, for example, or let's go 25, I really shouldn't use this calibration graph to find its concentration, because you can't really make a prediction, or you can't be certain that the relationship between concentration and peak area is going to remain linear beyond the point that you test. All right. Now, if you given this situation, so if you actually have an unknown with peak area of 25 and you want to determine its concentration, you have two choices here. You can either make a new calibration graph, which means that you have to create at least one more standard solution with a lot higher concentration, so a lot more concentrated, and hopefully the peak area of that particular solution is above 25, so you can extend this graph. Or you can just dilute your unknown sample, which is probably the more efficient and cheaper and less time-consuming way. So let's say if this is the unknown peak area, what I'm going to do is I'm going to dilute it by a factor of 2. So you're going to dilute it by, so you basically, say for example, take 1 ml of the sample and then add some water, some deionized water, so that the final volume is now 2. So you dilute it by a factor of 2. And if you do that, then hopefully, and it may not be exactly 12.5, but you should be able to bring the peak area down to within the range of the calibration graph. And once you determine the concentration of the diluted solution, you just need to double it to get the concentration of the original. So dilution is a very easy way to ensure that your sample is within the range of the calibration graph, and make sure that you don't extrapolate. All right, so because of that, I think it's worth recapping. I'm just going to leave this slide in the notes. I'm not going to go through it. We learned this last year, and it's going to come back with chromatography, and especially with the next topic, which is titration. But you need to understand how dilution and sampling works. There are multiple ways to think about it. You don't have to use a formula. Say, some people think about it very intuitively, and that's okay. But diluting is when you add water, so the number of mole of the solute is not going to change, which means that C1V1 equals to C2V2, with 1 and 2 being the two solutions. Sampling, on the other hand, is when you take a small portion from a stock solution. So when you take a small portion from a stock solution, the concentration should remain the same, and it means that N1 of V1 equals to N2 over V2. When you see a chromatography question, it's very likely that you're going to see both sampling and dilution, because what tends to happen is people will take a sample and then they dilute that sample, and then that sample is analyzed, and then you have to be able to work backwards to determine the concentration of the original substance, or sometimes they will ask for the amount of the original substance. Okay, because of that, the other thing that I think is worth recapping, and I'm not going to give you any lecture on this right now, because again, this is assumed knowledge, but you going to, we will expect that you can read, interpret, and calculate different types of concentration units. So I'm sure everyone is very familiar with the molar concentration or concentration in mole per liter, but there are other types of concentrations that may be asked. So I'm just going to leave some notes, just a quick summary of all those different concentrations again. Things like grams per liter or milliliter per liter are not very commonly used these days, but the main one that it's really used a lot is a percentages concentration. So percentage mass by mass, or percentage mass by volume, or percentage volume by volume. It's very important that you know what each of the unit means, and that you can actually calculate it or use it to work backwards if you have to. So molar concentration is here, but I also want to remind you of ppm and ppb, which might come back. And the main issue with chromatography questions in the exam is that students really struggle with concentration calculation. So it's worth having a quick look at this again, and we'll do some questions on this later. And that is the end of this video.